Good afternoon, everyone. We are Group 22, and today we'll be discussing about credit default prediction for American Express. So before diving into the Kaggle competition details, let's explore some backgrounds on Amex. So a statistic indicates that in 2023, there were 141.2 million active American Express cardholders, with 56.4 million in the US and 65.3 million internationally. This demonstrates that credit cards have become an essential part of today's digital era. And with a study done by the Federal Reserve Bank of San Francisco, credit card was used for 31% of payments in 2022, which resulted in a steady increase in delinquency rates, reaching to 3.1% at the end of 2023. Therefore, this leads to the challenge of the problem, which is how can we ensure financial stability and trust between card issuers and users? So for this competition, the main goal is to predict the likelihood that a customer will fail to pay their credit card bills in the future by improving existing credit default prediction models or developing new models and techniques to improve credit approval systems, enhance customer experience, and reduce risk exposure to lenders. So the dataset consists of 5 over million rows with 190 features that is categorized into 5 different kinds of features, which is the delinquency, spending, payment, balance, and risk. With all these features used to predict the likelihood of a customer owing to the future, using a binary classification of 1 to represent customer failing to pay and 0 to represent customer paying bills on time. Due to the large size of the dataset, data preprocessing was performed to reduce its memory footprint and improve data loading efficiency. The dataset was converted from CSV to the Packet format to enable faster reading and better memory handling. Missing values were replaced with 0 instead of being removed, preserving the dataset structure. Data types were also optimized, for example, converting float 64 to float 32 and integer 64 to integer 32 to further reduce any memory usage. Additionally, random noise was added to float columns to help distinguish continuous features from integer-based ones.
Before we get into feature engineering, our team uses two different types of features. One is overall feature, which is derived from the whole dataset, and the other one is recent feature, which is derived from the last 3 or 6 months.
In this stage, we perform comprehensive feature engineering to transform raw customer data into meaningful inputs for our machine learning model. Our approach is grouped into 4 key areas: numerical, categorical, date time, and additional features. Numerical features were aggregated using statistical functions such as mean, standard deviation, minimum, maximum, and last observed value. These help us understand both the typical and extreme behaviors of customers over time. For instance, the mean captures the average behavior, while the standard deviation reveals the variability in actions, which could indicate instability or consistency in behavior. Categorical features were summarized through count and unique and last. These metrics tell us how often certain behaviors occur, how diverse they are, and what the latest activity looks like. This is crucial for recognizing behavioral patterns or changes. Date-time features were derived from the timestamp column S2. We extracted attributes like month, day of the week, and computed 2 custom metrics. They span the duration of activity between a customer's first and last recorded actions, and days since last, which indicates how recently the customer was active. These time-based signals provide insights into a customer's engagement life cycle and recency of activity, both of which are key indicators of default risk. Additionally, we calculated trend-based features by computing the difference between the last and first values of numerical columns for each customer. This helps us capture the direction of behavioral change, whether metrics like spending or balance are increasing, decreasing, or stable. Additional pre-processing steps included grouping of features by customer ID to create customer-level aggregations. We also removed unused columns and adjusted data precision to optimize storage and computation. This feature engineering process ensures that our model is equipped with rich, informative features to accurately capture customer behaviors and make effective predictions. To predict customer default effectively, we experimented with 2 powerful and complementary models, the light gradient boosting model LGBM and a neural network.
We first begin with LightGBM, a gradient boosting framework that's highly optimized for large-scale tabular data. So why LightGBM? We chose LGBM because it's fast, efficient, and it supports categorical features natively. It's also ideal for handling the massive dataset provided in the American Express Default Prediction Challenge. We also employ a few key techniques. In order to speed up training, we use GPU acceleration, which parallelizes computations. Additionally, leaf-wise groups helps LGBM focus on high-impact splits, making the trees deeper and more accurate. And finally, histogram binning helps to reduce memory usage by grouping feature values into bins rather than processing raw data. To improve memory efficiency, LGBM bins histograms instead of using raw data and generates compact trees, which significantly lowers the memory usage, crucial for handling millions of records effectively. Finally, for the hyperparameters that we use, For tuning, we set the learning rate to 0.03 and the left max depth at -1 to allow for flexible tree growth, with a minimum of 64 data points per leaf. We also applied sampling to use 10% of features and 75% of data, resampling every 5 iterations. And to prevent overfitting, we included an early stopping after 100 rounds and used 7-fold stratified cross-validation for robust evaluation. Now, moving on to neural networks, which we use to complement LGBM by capturing complex, nonlinear interactions. So why neural network? Neural networks excel at learning feature hierarchies and subtle patterns, which is especially useful in high-dimensional behavioral data. So this makes them a perfect counterpart to our ensemble approach. So a few key techniques that we have used include designing the neural network with an input layer, followed by 3 hidden layers, size 2D, D, and 64, with D being the input dimension. We use ReLU activation for non-linearity and HE normal initialization to maintain stable gradients. To regularize and generalize better, we apply batch normalization and dropout after each layer. So, for training configuration, we use a binary cross-entropy loss function, ideal for binary classification, and optimized with Adam using a very low learning rate of 0.00001 to prevent unstable training. This setup ensures smooth learning and good generalization on unseen data. And finally, for output layer, it contains one neuron with a sigma activation, predicting the probability of default between 0 and 1.
Next, I will talk about the ensemble of our models and the performance. After exploring both our models, we decided to combine them and leverage their complementary strengths. Our ensemble method is weighted soft voting, where LGBM gets 0.5 of the weight, LGBM with predictions will get 0.1, and neural network gets 0.4. We gave more LGBM weight because of its higher individual accuracy. We also use these 5 models from the 5-fold cross-validation in the training process for each type of model. With the above strategies, this can ensure better generalization and robustness on unseen data. Now we will talk about the model strengths. LGBM gives strong tabular performance, native categorical handling, high overfitting resistance, and clear interpretability. While neural network is superior at modeling nonlinear relationships and sequential patterns, but it needs extra tunings and encoding. For the model performance, our team achieved a private score of 0.8063 and a public score of 0.79852. And our performance ranking is 1,994 out of 4,876, which is around the top 40.8% of the competition.
So for the key challenges of our project, firstly is the data size and memory management. As we are working with 5.5 million rows, it requires memory optimization and smart data type handling to prevent clashes. Second is the GPU and CPU compatibility issues. Memory limits on the GPU force a fallback to the CPU processing, impacting training speed and pipeline consistency. Third is the feature engineering complexity, as unknown features make it hard to derive meaningful signals, requiring extensive EDA and manual tuning. Fourth is the model output misalignment, which refers to different prediction index orders leading to incorrect outputs. This can be solved by enforcing consistent sorting via customer ID. Lastly is the limited compute resources, as it's constrained by 16 to 30 GB RAM, requiring lightweight models and careful memory control throughout the workflow. In conclusion, our final model employs an ensemble of light GBM and neural network. For LGBM, it utilizes GPU acceleration, lift-wide growth strategy, and out-of-fold predictions, while the neural network incorporates 3 hidden layers. Other contributions to improving the model includes efficient memory handling and feature engineering. Our key takeaways is understanding the importance of managing memory usage, ensuring consistent indexing during model merging, and leveraging ensemble learning to enhance overall accuracy. So this is the end of our project. Thank you.